All right, here's a couple of good exponential equations. So the first one says the population of West Goma was modeled by this function, and East Goma modeled by that function, and x responds to the number of years. Assuming trends when will the populations be equal? So what they're asking is, when will f of x be equal to g of x? So they want to know when the populations are the same. Well, f of x is equal to 17.1 e to the 0.0017x, and g of x is 13.8 e to the 0.0133x. Okay, so now I've got to solve this equation. I've got a couple issues. Like, I'd like to use the log both sides thing to be able to pull the exponent out to the front, but I have a product there, so I can't really do that initially. I guess what I could do is take the log of both sides. Will this work? Oh, let's try it. There's a couple ways, but let me try this. Why don't I take the ln of both sides? So not log, but ln. So I'm going to take the ln of 17.1 e to the 0.0017x. And if I do it to that side, I have to ln the other side. 13.8 e to the 0.0133x. Okay, now I'm taking the ln of a product. So the rule is, if I'm taking the ln of, say, a times b, that's the same as ln of a plus ln of b. Okay, so I can go ln of 17.1 plus the ln of e to the 0.0017x is equal to, same thing over here, ln of 13.8 plus ln of e to the 0.0133x. Now where's my calculator? I can figure out that ln of 17.1, and I'm sure there's other ways to do this, but let's just do that for now. Calculator, where's my ln button? Ln of 17.1 equals 2.839, let's call it, plus, now this is the same as log base e of e to the 0.0017x. And we said if these are the same, then the answer to this whole expression is just 0.0017x plus 2.839. Now I'm getting somewhere. Is equal to, okay, ln of 13.8. Ln 13.8, go, is 2.6247, let's call it, plus, same thing will happen here, 0.0133x. Now let's gather the x's. This one looks bigger, so let's bring them onto this side. So 0.0133x minus 0.0017x is equal to 2.839 minus 2.6247. Okay, let's subtract those. 2.839 subtract 2.6247. So on the left side I get 0.2143, and on this side 0.0133 minus 0.0017. So this is 0.0116x. Now I'm solving for x, so I need to divide both sides by 0.0116. Divide 0.0116. So 0.2143 divided by 0.0116 equals, I'm getting 18.474-ish. So let's see what this says in the question. can estimate what the population will be when the... Assuming these trends continue, estimate what the populations will be when the populations are equal. Well, that's an even tougher question. This is a fairly tough question to begin with. But X is number of years. So I'm saying about 18 and a half years, that's when the populations will be equal. So now, and you can test this, I'll just do it on one, but you can test on the other one too. Let's go back to the function there. I'll just do it off to the side here. They say g of x is equal to 13.8 e to the 0.0133x. So I'm going to plug this in for x. So the value of the function g, when you plug in 18.474, will be equal to 13.8 e to the 0.0133 times 18.474. Okay, so on my calculator, 13.8, and then e to the, and I'm going to put this in brackets so it keeps it as an exponent, 0.0133 times 18.474. See, yeah, that looks right. Go. All right. So that's an interesting number. Yeah, I come up with 17.6435. So that's a population. Now, is the population in millions or something? Oh, it's in millions. So it'd be 17.6435 millions. So if you were to take this number here, you might not be able to see that, the 18.474, and if you were to plug it in here, you should get the same number. Try it and see. Okay, so that's one. Let's try another one. So question 25 says, solve for x, so 27 to the x and 10 to the minus 3x. I see 27 and I'm automatically thinking 3 to the 3, so that'd be 3 to the 3x is equal to 10 to the minus 3x, but I can't make those bases the same. So doing that, yeah, it'll work and that would still be fine, but probably doesn't help me any. So let's just do the same thing as we did on the last question. To get at those exponents, let's log both sides. Since this is base 10, I'm going to use log base 10. So it'll be log base 10 of 27 to the x is equal to log base 10. Maybe I'll put the base in. No harm in that. Log base 10 of 10 to the minus 3x. Okay, so we've learned that I can bring that exponent out to the front. So it'll be x times the log base 10 of 27 is equal to negative 3x times log base 10 of 10. Now log base 10 of 10 is just 1, so this stuff on the right side is just negative 3x. Then on this left side, I've got log of 27. Let me figure that. That's probably 1 point something. Log base 10 of 27. 1.43, call it. 1.43 times x. I'll just put the x at the back. I have x on each side, so I should get them together. Let's add 3x to each side. So on this side I have 4.43x is equal to 0. Well, that's awkward. We'll divide both sides by 4.43. And so I get x is equal to 0. So that's the only number for which that function would be, not for which it would be defined, but that's the only number that would make that statement true. Let's just check that. It seems funny, doesn't it? 27 to the 0 is equal to 10 to the minus 3 times 0. So anything to the 0 power is equal to 1, right? And then 10 to the negative 3 times 0 would be 0. Oh, and 10 to the 0 is 1. 1 is equal to 1. Yeah, it checks out. Good one. Let's try a couple more. How long will it take a sample of radioactive substance to decay to half its original amount if it decays according to this function, where t is the time in years rounded to the nearest hundredth? And they want to know when it's going to decay to half of its original amount. Well, this is sort of written in this form. We have P of t is equal to P0 e to the k times t, right? And so this number here, what I'm looking at, is that's probably the initial amount. That's 650, because that's what a P0 is. And that's in that slot, right? So they want to know how long it'll take to decay to its original, half of its original amount. So if the original is 650, half, this number here, would be 325. So 325 is equal to 650 e to the negative 0.129 t. Divide both sides by 650. Of course, I'm going to get a half on this side is equal to e to the negative 0.129 t. And now let's change form from exponential form to log form. So it'll be log base e of 1/2 is equal to negative 0.129 t. Okay, log base e is the same as ln. So ln of 1/2 divided by negative 0.129 is equal to t. And there what I did is I just divided both sides by that stuff in front of the t. Okay, so calculator. So I'm going to go ln of 0.5 and my bracket divided by negative 0.129. Go. So the time I'm getting is 5.37. And they want to the nearest hundredth? Yeah, I'd be right there. So it'll take just over 5 years for that radioactive substance to go from 650 grams, or whatever they're weighing it in, down to 325. It'll take that long. Last one. Ooh, I like this one. Bacterial culture has initial population 10,000. Let's just write our formula. P of t equals P0 e to the kt. If the population declines to 5,000 in 8 hours, okay, hold on here. So initially it's 10,000. I'll put that in here. And then they say it goes down to 5,000. Here's 5,000. And it does that in 8 hours. E to the k times t is 8. Now, before I even read any more, okay, so don't even look at this rest of this stuff. We'll bring it back. But before I look at any more, I can solve for k, because I have everything except for k, right? E is a number, 2.71828, etc. So I can solve for k. Let's first divide both sides by 10,000. So I get 1/2 is equal to e to the, we'll call that 8k. Change it to log form. Log base e of 1/2 is equal to 8k. Log base e is the same as ln. So this is ln of 1/2, or 0.5, whatever, divided by 8. That's going to be equal to k. So really what I'm finding here is the constant of change. And it's declining, so my k value better be negative. Because if it's declining, k should be negative. Let's try. Ln of 0.5 bracket divided by 8. Oh, yeah, perfect, negative. So my k value is negative 0.086643, and it keeps going. So that's my k value. Okay, now maybe I should read a little bit more of the question. Okay, let's read that. It says, what will it be at the end of 10 hours? Well, I can figure that because I know what it starts at. Let's put our formula in again. So P of t is equal to how much they start? E to the k times t. So they want to know how many there will be at the end of 10 hours. That's this. So what is the population after 10 hours? Is equal to how much they start with. Still starting with 10,000. E to the k, I just found that out. So it would be negative 0.086643 times the time. This time my time is 10 hours. So times 10. Well, I don't have to do any log form at all. I just plug this in. So 10,000. And then the e to the, and then in brackets I'm going to put negative 0.086643 times 10 bracket go. So the population after 10 hours is going to be 4,204.5 about. It doesn't tell me where to round it, but that would be sort of what it would be. And this would be a population, so that's how many of this bacteria there would be. So it's declining. Let's just see if it makes sense. Goes from 10,000 to 5,000 in 8 hours. So after 10, I should have less than that. And I have less than that, so that makes sense. Okay, those are 4 really good questions. Tough questions.